Here we have a conceptual question about conservation of energy. And so we have a situation where there's 3 tennis balls, all thrown off of a cliff at the same time. Each one's thrown with the same speed, but they're thrown in different directions. And so we first want to rank the final velocity of the tennis balls when they hit the ground from least to greatest and explain our answer. Well, if we think about it, they all start with the same gravitational potential energy and the same kinetic energy, which means when they hit the ground below at the same location, they'll all end with the same velocity because they'll all end with the same kinetic energy. In terms of an explanation, the first thing I'm going to say is that all 3 start with the same initial kinetic and gravitational potential energy, and that comes to the fact that they have the same height and they have the same velocity. When they hit the ground, they'll end with 0 height. Okay, so we'll say the ground down below here is a height of 0. They'll end with 0 height, which means that they'll have all kinetic energy, and will be the same final kinetic energy because they started with the same initial amount of energy. And that means they're going to be traveling at the same speed. For part B, we want to rank the time that they're in the air from least to greatest. And so for that, we're going to think about their initial y velocities. So A has a positive initial y velocity, B has a negative initial y velocity, and C actually has 0 y velocity in the beginning. So time-wise, that will affect how long it takes to hit the ground. The first one to hit the ground is going to be B because it's traveling downwards initially, and that's going to hit before C, which has no initial velocity in the y, and that's going to hit before A, which has to travel up first and then fall back down. For this next one, we're going to consider the motion of a comet as it orbits the sun, which we see as highly elliptical. And as we learned before, Kepler's second law tells us that it's traveling fastest here when it's closest to the sun, and slowest here when it's furthest away from the sun. We want to explain why this is true in terms of energy. The first point that I would make here is there's no work being done here by non-conservative forces, so the total energy of the comet is the same throughout. The next point that I would make is that when it's here closest to the sun, it has the smallest amount of gravitational potential energy and therefore the greatest amount of kinetic. So as it's undergoing this orbit, we have this transfer of energy between those two, from gravitational potential energy to kinetic and back. So when we're here closest to the sun, we have the smallest gravitational potential energy and therefore the most kinetic. As we go all the way out here to our furthest point, we have the greatest gravitational potential energy and therefore the smallest kinetic energy. And that kind of continues back and forth throughout this orbit. Moving on to part B, we want to know if the total energy of the comet by itself changes. And the answer to that is yes. The comet only has kinetic energy, and since the kinetic energy is changing, the total energy of the comet will change. This just really gets to that idea that gravitational potential energy is stored between the comet-sun system. For part C, we want to now know if the total energy of the comet-sun system changes. So now we are including that gravitational potential energy. And so the answer here is going to be no. No work is done on the system by non-conservative forces, and that means that the energy just transfers between kinetic and gravitational potential. So for this next one, we have a roller coaster that's going along the track here, and the first thing we want to do is set up our energy bar chart, showing its energy as it goes from A to B to C. So starting at A here, we have only a height, we're not moving, so there's no kinetic, and there's no springs involved, so our only energy is going to be gravitational potential energy. So we'll say that we have 4 bars of gravitational potential energy here at A. As it transitions down here to B, I'm going to say my height is 0 here down at B, and so that means it's only going to have kinetic energy there. So those 4 bars of gravitational potential are going to become kinetic here. There's no work being done because we're ignoring frictional forces. The only force we have is gravity, but that's a conservative force. So all 4 bars of energy will now be kinetic at B, and then we're going to transition up to C here, where our height is 3/4 h. So if we want to be really technical, we have 3/4 as much gravitational potential energy as we did at A, so that's going to be 3 bars of gravitational potential at C. and the rest is going to be kinetic. Once again, we're going to ignore frictional forces, so our total energy is going to be 4 bars based off of the scale I used. Obviously, you can change your scale, and you don't necessarily have to use the exact same one that I did. Moving on to B here, we're going to set up conservation of energy to determine the velocity at point B. So we'll say E initial plus work is equal to our final energy. And as we just saw, we start with purely gravitational potential at A, and we end with purely kinetic at B. So we can say mgh equals 1/2 mv squared. Our masses here are going to cancel out, and we can go ahead and solve for that velocity. So it's going to be 2gh equals v squared, so our velocity is just the square root of 2gh. For C, we're going to set up our conservation of energy once again to get the velocity here at point C. We do have two options. We can either go from B to C or from A to C. I'm going to go from A all the way to C. So I'm going to start here at A with just gravitational potential energy, although you could start at B and go up to C. I'm going to say there's no work being done because we have no non-conservative forces, and so we're going to end with our final gravitational potential energy at C plus our kinetic energy at C. So we can fill in the formulas we know for those energies. The mass here once again cancels out, and I'm going to say my initial height was just h, my final height was 3/4 h plus 1/2 mv squared. We can subtract that term there and we get 1/4 gh equals 1/2 mv squared. So that means that gh over 2, okay, multiplying both sides by 2 here, equals v squared, so v is the square root of gh over 2. For this next one, we are launching a box using a spring along a frictionless surface, and it's going to slide up to some height here at C. We once again want to start with our energy bar chart. So initially we have a spring being compressed at point A here, and so we're going to start with spring potential energy. I'll go with my default here and say we have 4 bars of spring potential energy there at A. That spring potential energy, as that spring is released, is converted to kinetic here at B. And since there's no non-conservative forces, we're going to have 4 bars of kinetic energy at B. And then the object slides up to a height here at C. And so that's going to transfer into gravitational potential energy, eventually coming to a stop. So that means all of it, all 4 bars, will be gravitational potential energy at C. For the next part, we're asked if the spring is tripled, how that affects the velocity at point B. So this is one where we're going to set up our new and our original. Okay, and we're ultimately answering in terms of our original velocity v. So in our original situation, we start with spring potential energy, and it becomes kinetic, and we're just thinking here about this transition from A to B, not thinking about point C at all yet. So we can say 1/2 kx squared equals 1/2 mv squared. So that's our original situation. In our new situation, we're going to triple that distance compressed. So it's still going to be spring potential energy becoming kinetic, but now we're going to say 1/2 k times 3x, that entire quantity squared, equals 1/2 m, and I'm going to say v prime now squared. What I can do is I can actually get rid of the 1/2s in both equations. And what I'm going to do is I'm going to do my trick where I divide the two equations. So I'll take my new one, which is going to be k times 3x squared, or 9x squared. That's equal to m times v prime squared. And that's going to be over divided by k times x squared, which is equal to m times v squared. So we'll divide those two equations. The k's go away, the m's go away, the x's go away, and what I'm left with here is 9 is equal to v prime squared over v squared. When I go ahead and solve for v prime, I get that v prime is equal to 3v. All right, just multiplying both sides by v squared and then taking the square root. So our new velocity is going to be 3 times as much as our original. Moving on to the second part, we now want to think about our height at point C. So we're going to be going from the beginning all the way up to that height. and thinking about ending with that gravitational potential energy. Once again, I'm going to set up my new and my original. Now, though, it's going to be spring potential becomes gravitational potential. So originally, it's 1/2 kx squared equals mgh. In my new setup, it's still going to be the same energy types, but it's going to be 1/2 k times 3x, that quantity squared, equals mg, and now it's going to be h prime, which is what I'm ultimately looking for. Once again, I'm going to divide these two equations, so I'm going to take this 1/2 k, and that becomes 9x squared, all right, equals mgh prime, and I'm going to divide it by 1/2 kx squared, and divide the other side by mgh. A bunch of things are going to cancel out here. The 1/2, the k, the x squared, the m, and the g all cancel out. And so what I end up getting is 9 is equal to h prime over h. So that means that h prime, my new height, is 9h, 9 times my original height. For this next one, we have a situation where Clark Griswold is sledding down a hill on a saucer in Christmas Vacation. If you haven't seen the movie, you should. It's a classic. Okay, and he puts a special substance here on the saucer to reduce the frictional force to 1/10 of his weight. All right, what we ultimately want to know is how fast is he traveling at the bottom. So we, of course, are going to use energy here to set this up. E initial plus work equals E final. So let's first think about what we have energy-wise. We start at the top of the hill here with some height, so we have gravitational potential energy, and we're at rest initially. We get to the bottom of the hill traveling with some velocity, so we have kinetic energy, and in between we have some amount of work being done by friction, because we do have this frictional force here. So our energy setup is going to be UG plus that work done by friction equals K, our final kinetic energy. And then we can start filling in the equations we have for those various energies. So there's our setup. We do have a few things we can do here. Number one, we don't know the height, but we do know this length and we do know that angle. So that means that this height here is just going to be d sine of theta, basically the y component of that distance. We also know that our frictional force is 1/10 of our weight. Okay, so 1/10 of mg. Okay, keep in mind that it says weight, not mass. Weight is the force of gravity. So we can substitute in those things into our equation here. Alright, so now I'm just going to simplify this sum mathematically, so I notice that there's an m in every single term, so I can cancel out that m from all the terms. I also see that both of these terms on the left-hand side have a g and a d in them, so I can factor that out, and what I'm left with then is just sine of theta plus 1/10 times sine of 180, which is -1, so really just -1/10, and that's equal to 1/2 v squared. Multiply both sides by 2 and take the square root, and I get that 2gd times sine of theta minus 1/10, square root of that entire quantity, is equal to v, and there's my final answer. Alright, moving on to this next one here. This one's about power. So we have two blocks that are the same size and mass are being pulled across floor at a constant speed. So both have a pulling force here, and there's friction in both cases between the block and the floor. So they also both have a frictional force going back in the opposite direction. And so the first question asks which one has a greater pulling force acting on it. Thinking back to what we know about friction, friction really depends on the coefficient of friction and our normal force. Since they're made of the same material and they have the same mass, both of those are going to be the same, so that means they have the same frictional force acting on it and therefore the same pulling force because they're being pulled at a constant speed. So in both cases, that pulling force is going to be equal to our force of friction. For part B, it asks, in a given time, which block has a greater power delivered to it by the pulling force? So for that, I'm first going to think about my work being done, because power is the rate at which work is being done. And so I see here in this equation that the force, obviously, is the same for both of them. However, my displacement is going to be greater for the block that's moving faster. Okay, and so that means that block A will have more work being done on it because it's moving faster, and therefore it travels a greater distance in a given time, and so more work is done on it. So for this next one, I have a problem here about a bicyclist in the Tour de France who can output an average power of P. Okay, and we know that this cyclist starts at the bottom of a hill at rest. So there's my cyclist. They have a mass of M, and they travel up to the top of this hill that has a height of H. And when they reach the top, they're traveling at a speed of V. And we want to know how long it takes them, or we want to derive an expression for the time it takes them to get to the top in terms of the things that we're given here. So the first thing I'm going to do is I'm going to think about my work being done here, and I'm going to think about the fact that work is the change in energy, meaning that it's E final minus E initial. So I think about my energy. In the beginning, I don't have any energy because I'm not moving. I have no height, so that initial term is just 0. And when I get to the top, I have gravitational potential energy because of the height and kinetic. So that means that my work done is simply my gravitational potential energy plus my kinetic, and I can substitute in for those two things. So I have mgh plus 1/2 mv squared, and that's going to be my work being done in this situation. Now that I have my work being done, I can think about my power, which is work over time. So I know my power here is P, and that's going to be equal to mgh plus 1/2 mv squared all over t. And if I solve for t, the best way of doing this is just to cross multiply. So I can say pt equals mgh plus 1/2 mv squared. And that means that my time here is going to be mgh plus 1/2 mv squared, all divided by p, my power.